Welcome to the Explainer. Let's just jump right in, shall we? Today, we're looking at a massive fundamental tension right at the heart of modern artificial intelligence. The big question is, how do we make our phones incredibly smart without exposing our private data to the cloud or, completely draining our cellular bandwidth in the process? It's a huge challenge. But today, we're breaking down a fascinating paper that claims to have definitively solved it, using a framework called SSTQ. So picture this core problem in your mind. Think about the predictive text on your keyboard or that facial recognition sorting your photo album on your phone. How can a massive central AI model actually learn from all of our collective behaviors, our text messages, our photos, without companies like Apple or Google ever actually seeing or storing those raw, highly private images on a central server? Basically, how does the AI learn from you without actually seeing you? Well, the answer usually relies on something called Local Differential Privacy, or LDP for short. You can think of LDP as like a mathematical blur filter applied right on your device before a single byte of data ever leaves your phone. By injecting carefully calibrated statistical noise into the data, the server gets this completely jumbled, noisy information from you, and that gives you total plausible deniability. The server literally cannot reverse engineer your specific data. But when it aggregates the noisy data from millions of other users, the noise cancels out and the true underlying patterns emerge. Sounds pretty perfect, right? Well, actually, no, not quite. And this perfectly sets up the core issue we're tackling today, the trilemma. In the world of federated learning, which is where AI is trained across thousands of mobile devices, you historically could only pick two of these three competing needs. You want high accuracy for your AI, you want strict privacy to protect the user, and you desperately need communication efficiency because, let's face it, cellular bandwidth is expensive and limited. Until now, optimizing all three of these simultaneously was just considered mathematically impossible. To see why it's so hard, let's look at the baseline methods with a quick Goldilocks analogy. On one side, we have an approach called PrivUnit. Now, PrivUnit is fantastic at maintaining privacy and accuracy, but it is way, way too heavy for a standard data plan. It requires transmitting these massive, uncompressed continuous data vectors. On the flip side, we have VQSGD. Now, VQSGD is highly communication efficient. It compresses data really aggressively using rigid geometric shapes, but it is incredibly fragile. When the data gets complex, the accuracy just shatters completely. Let's actually zero in on why VQSD fails, because honestly, it's kind of the villain of our story here. The researchers prove that VQSG suffers from what they call a fundamental dimensionality curse. As the dimension of the data grows, say you're moving from a simple text model to a highly complex image recognition model, the statistical variance, or the error of VQSG, just explodes. It hits this massive cubic variance growth rate. The math is super clear on this. The rigid geometry used to compress the data shrinks the privacy probability gap, and that causes the error to spiral totally out of control. It's essentially a dead end for modern complex AI. So, enter the hero of today's explainer, Subsampled Stochastic TurboQuant, or thankfully, SSTQ for short. This is the mathematical breakthrough framework proposed by the researchers, and it elegantly solves the trilemma. By completely decoupling the size of the compression codebook from the ambient dimension of the data, SSTQ basically catches our villain and neutralizes that curse of dimensionality once and for all. Okay, so how does it actually pull this off? Well, it breaks down into three pretty elegant steps. First, it spreads the signal out evenly using redundant Cation bounding. Second, it uses oblivious subsampling to randomly pick just one single piece of that spread out data. And third, it applies a flat randomized response to add that crucial privacy noise. Imagine the AI's gradient data is an incredibly detailed, massive jigsaw puzzle. Instead of trying to send the whole puzzle over the network or a badly squished version of it, SSQ processes it so perfectly that we only need to send just one single perfectly representative, encrypted puzzle piece. Now, the math behind that first step, caution representations, is actually super fascinating. It utilizes an overcomplete equal norm tight frame. Now, if that sounds like incredibly dense math, think about it using a peanut butter analogy. Normally, data can be chunky, right? Some coordinates hold massive amounts of information, while others hold absolutely zero. Caution frames act as an algorithmic signal spreader. It spreads the data perfectly and evenly across a slightly larger mathematical space. By doing this, it mathematically guarantees that no single byte or coordinate holds too much sensitive information. It's all smooth. And because that cache-in frame just leveled out the signal perfectly across all the coordinates, we don't have to send the whole vector anymore. We can randomly subsample just one single scalar coordinate, and it will still be mathematically representative of the whole thing. This means the client device only needs to transmit two tiny pieces of information: the index number showing which coordinate was picked, and the quantized scalar value of that coordinate itself. And the absolute best part? This entire process is completely data oblivious. I mean, the theoretical weight of this breakthrough really can't be overstated. The authors prove that SSTQ achieves the optimal theoretical mean squared error scaling. That means it perfectly matches the best possible accuracy limits of LDP while simultaneously achieving extreme, almost unbelievable compression. The communication payload drops to literally just the logarithm of the frame size plus the tiny bit widths of the codebook. Let's put that abstract math into perspective with one concrete number: 20. For a complex neural network model trained on the Fashion MNIST dataset, a standard uncompressed method requires transmitting over 814,000 bits per client per round. SSTQ slashes that massive payload down to just 20 bits. Not 20 kilobytes, just 20 bits. That is an astronomical reduction in bandwidth without sacrificing a single ounce of the mathematical privacy guarantee. But, the researchers didn't just stop there. For situations that require even higher precision and denser codebooks, the standard randomized response noise can sometimes introduce a bit too much variance. So they turbocharge the framework by swapping in a metric-aware Laplace noise injection. Basically, this turbocharged step lets us pack even more accuracy into our tiny little signal. Instead of flatly randomizing the output, the metric-aware variant uses continuous truncated Laplacian sampling, and then maps that to the nearest deterministic code word. Now, what this means in plain English is that it strategically trades a tiny, mathematically bounded amount of localized bias in exchange for vastly reducing the variance. It prevents the error from just exploding when you try to use higher bit widths, and that enables incredibly efficient multi-bit quantization. So the theoretical math checks out. It's flawless. But how does it actually hold up when we plug it into real-world federated learning benchmarks? To prove their claims, the researchers tested SSTQ against those baselines we talked about on two standard image classification tasks. First, Fashion MSIET, which has about 25,000 parameters, and then CFAR10, which scales things up drastically to nearly 100,000 parameters. All right, here is the ultimate proof. We've got a lot of data here, so let's break it down carefully. We're looking at training loss on the left and test accuracy in the middle. The top row is tracking Fashion MNIST, and the bottom row is tracking that much more complex CIFAR10 dataset. Notice that solid black line? That is the clean, non-private baseline. Right below it, tracking almost perfectly, is the blue line, PrivUnit. Now, PrivUnit achieves great accuracy and low loss, sure, but remember, it transmits millions of bits, making it practically useless for mobile networks. Now, trace the path of the red line, VQSGD. On the training loss charts on the far left, that red line just wildly diverges, spiking upwards totally out of control. On the accuracy charts in the middle, the red line completely flatlines near the bottom. It fails entirely, all because of that dimensionality curse we talked about earlier. But now look at the purple and orange lines representing our SSTQ framework. They track beautifully alongside the dense PrivUnit and the older SKR methods. They achieve fantastic accuracy and steadily decreasing loss, completely avoiding the catastrophic failure of VQSGD. Now I want you to direct your attention specifically to the two charts on the far right, because these are the money shots. This is accuracy versus communication costs plotted on a logarithmic scale. The absolute holy grail here is the top left quadrant. You want the highest possible accuracy on the y-axis combined with the lowest possible bitrate on the x-axis. Look at where PrivUnit is. That blue square stuck way over on the far right at nearly 1 million bits. Look at V2SGD, the red triangle, trapped way down in the bottom left. Sure, it has low bytes, but absolute garbage accuracy. Now look at the crosses representing SSTQ. They sit perfectly in that top left quadrant. They achieve the incredible test accuracy of the dense models, but they sit astonishingly far to the left on the bitrate scale. It's exactly where you want to be. Let's just definitively drive this efficiency point home by looking at the raw numbers in this table. To achieve that top-tier accuracy on CIFAR10, PrivUnit requires over 3.1 million bits per client. The closest competitor that actually functions, SQKR, requires 72 bits. SSQQ, it requires exactly 22 bits. That is literally less than a third of the bits of its absolute closest competitor, all while maintaining optimal accuracy and strict mathematical privacy. I mean, it is an absolute masterclass in data compression and privacy preservation. So,
that leaves us with a pretty massive question. With this mathematical bottleneck of privacy and cellular bandwidth definitively solved by SSTQ, what is the future of on-device AI? Just imagine a world where every smart device you own is constantly training hyper-personalized, incredibly powerful AI models directly from your daily habits. But a world where it is fundamentally, mathematically impossible for those tech companies to leak your private life. That future? It isn't just theoretical anymore. This paper proves the math is already here. Thanks for joining me on this explainer, and I'll catch you on the next one.